Welcome to this video on SN2 reactions. SN2 is a one-step reaction, but its rate depends on both the electrophile and the nucleophile. So what do I mean by one step? Well, one step means that the nucleophile attacks that carbon that bears the leaving group, and the leaving group leaves at the same time. So these things are happening simultaneously. The nucleophile attacks and the leaving group is leaving at the same time. They are concerted, you could say. So they are concerted. So how do we know if we have an SN2 reaction? Well, if the carbon that bears the leaving group is primary, we're going to have SN2. Secondary, we can do an SN2 reaction, but this is kind of trickier because that depends on the reaction conditions, because it could even be an SN1 reaction, but I will make a video on how we determine if we do SN2 or SN1. But if it's a primary, we're doing SN2. If it's secondary, we can still do SN2, but we cannot do SN2 on a tertiary carbon. The reason being is because this carbon is too sterically hindered for that nucleophile to attack it. So sterically hindered. So this is not going to happen. We're not going to attack this. It's too bulky. That's what sterically means, really. Too many groups attached to this carbon, so it can't attack it. So it's not going to happen on a tertiary. That's why I have all these like less than arrows for that tertiary. It's not going to happen. So another way to determine if we're doing an SN2 is the nucleophile that we're using. If we have a strong nucleophile, such as sodium hydroxide, sodium cyanide, chances are we're doing SN2. And a tip to, when you do these problems, an important tip is that if our carbon has a stereochemistry, such as this carbon has a wedged bromine, we are going to do an inversion of configuration, where this wedged becomes a dashed when our nucleophile attaches. So this is wedged, it's going to become dashed, and our nucleophile is going to be on that dashed. And this is called inversion of configuration, and the reason that happens is because we do a backside attack. So this is backside attack. Okay, let's do some examples so this will make more sense. Okay, let's do some examples now. So in this first example, we have this hexane ring with a wedged bromine. So what is the first thing that happens in SN2? Well, our nucleophile attacks simultaneously as our leaving group leaves. So how are we going to show that? Well, a good tip is to remove this sodium ion. Just get rid of that. Sodium ions have a plus charge, so obviously this cyanide is going to have a negative charge. So what this cyanide looks like is we have a C bonded to an N with a lone pair on the carbon, 1, 2, 3, 4, 5. This carbon bears that negative charge. Now this carbon with the negative charge is going to attack backside to this bromine, and it's going to kick that off. So we represent our product like this. A dashed cyanide joining right there. So what else do we need to show? Well, you don't really need to show, it just depends on your professor. Remember, we had that sodium cation and this bromine anion left because it took both of those electrons in this bond. So you could represent it like this, a sodium cation bonded to a bromide as your other product. But this is the important one, which your professor is going to want to see. Let's look at this one. It looks complicated, but it's really not. This carbon secondary, we can still do, wait, it's not secondary, it's primary, sorry. This carbon is bonded to one carbon, so it's primary. This carbon was secondary, though. So this is primary, we can do that. Let's get rid of this sodium, and let's just do OH with the minus on the oxygen, because we know that's what hydroxide looks like. So it's going to attack backside, and our bromine is going to be kicked off, and we'll get something that looks like this. We have our chain, 1, 2, 3, yep. And then we have our OH that attached. Once again, you could put NABR as your other product, but that's not important. What's important is this guy right here. So that really does it for this video on SN2. It's really simple. It's concerted. The main thing is SN2 is concerted. The rate law, I didn't really talk about that, but the rate law says it depends on the electrophile, which is the one that bears our leaving group, and that would be, I'll just put it E for electrophile, and it also depends on the nucleophile, which was the cyanide and the hydroxide, so I'll just put it NU for nucleophile. So it's concerted, meaning one step, so one step. The rate law says it depends on both the concentration of electrophile and the nucleophile, and inversion of configuration because of backside attack. So inversion of configuration. So I hope this video helped you. Please leave a comment if you need help. Give it a thumbs up and subscribe. I'm going to make a video on some more examples for SN2 and SN1, how we determine which one do we use. So yeah.